Okay, chemistry gang. This video, I know I got a couple videos on stoichiometry, but this kind of video is just, um, very much just an introduction to stoichiometry. So by now, in this video, it's kind of understood that you know how to do your mole calculations. So you know all your mole map stuff, including molarity calculations, volume of a solution, molarity, how do you find moles. So being able to use your mole map, converting grams to moles, liters of a gas at STP to moles, particles to moles, or vice versa, and then also liters of a solution times the molarity to get moles of the solute, or moles of the solute divided by the molarity to get liters of solution required. So if you don't have a solid understanding of how to do those mole conversions, then you need to go back and review all the mole calculation stuff before you start thinking about stoichiometry. Because all stoichiometry is going to end up being is basically similar dimensional analysis setups to to the way we do mole conversions. So it's going to look kind of the same, but there's one more little step that you have to do. So you're going to be doing mole conversions, that kind of thing, and then there's one little step in there that makes it stoichiometry and not just a regular unit conversion. Okay, so we're going to go through that in this video, stoichiometry, the fundamentals of it, and then understand that we're going to build on to this. But a stoichiometry problem, once you recognize you have a stoichiometry problem, there's 4 steps to follow. You follow those steps, you get the right answer every time. Okay, so let's dive into it. All right, so stoichiometry, what are we doing? Here we go. All right, so what you need to understand is if you ever followed a recipe, like you were making cookies with your mom, or baking cake for the bake sale or something, if you know how to follow a recipe, if you know how to tweak a recipe to make it, and so if it's a recipe for 2, but you're serving a dinner of 10, and you know how to tweak the recipe, you've been doing stoichiometric calculations. That's what stoichiometry is, following a recipe. And so when we get to the steps, you're going to find that step number 1 is always know what the recipe is. All right, but the key to following the steps of stoichiometry is knowing when you have a stoichiometry problem. And it's real easy. Okay, you're going to follow your steps for stoichiometry when the question gives you the amount of one substance, we'll call it substance A, but it asks to find the amount of substance B, another substance. That's stoichiometry, right? So if I tell you how much oxygen reacts and I want to know how much water can be produced, that would be stoichiometry. I give you an amount of oxygen and I ask for an amount of water. I'm giving you the amount of one substance, you're asked to find the amount of something else. That's when you follow your steps for stoic. So let me show you what just a regular mole calculation looks like. So this question here, how many oxygen molecules are in a 50-liter sample of the gas at STP? This is not stoichiometry. This is converting liters of oxygen gas to molecules of oxygen gas. The substance isn't changing. This is just a mole conversion, okay? So we already know how to do this setup, right? We would take our 50 liters of oxygen gas that's at standard temperature and pressure, divide by 22.4 liters, that'll cancel out liters and give me moles of oxygen gas, O2, and then multiply by Avogadro's number to get particles, and because O2 is a diatomic molecule, the particles are molecules, all right? So all we have to do is divide by 22.4 and multiply by Avogadro's number, and that would give us our answer. This is not stoichiometry. It's dimensional analysis. It's unit conversion, okay? But we're not changing the value of anything, right? What we're doing is we're saying 50 liters of oxygen gas is equal to this many molecules of oxygen gas. That's what we're saying. This thing and this thing are the same. It's just a different way to show it, right? It's like 1 kilometer, 1,000 meters. It's the same thing, okay? So this isn't stoichiometry. So let's look at what a stoichiometry problem would look like, okay? This would be a stoichiometry problem. how many oxygen atoms, not molecules, atoms, are in a 50-liter sample of the gas. So since we know oxygen means O2, right? This question, right? If we did this calculation, notice the answer is molecules of oxygen, but here we want atoms of oxygen. So we're looking for a different thing. We're looking for a different substance. We're given liters of oxygen molecules, but we want to figure out total oxygen atoms. This would be stoichiometry, and that's kind of the difference. This one isn't that obvious, but I wanted to show you. This would be a stoichiometry problem. So let me show you the setup to answer this question, okay? So just like the first question, we're going to take our liters of oxygen, O2, and divide by 22.4, and that's going to give us moles of oxygen, right? But then what we're going to do is use our recipe. Our recipe is the chemical formula for oxygen, O2. It's telling us that there's 2 oxygen atoms in 1 molecule of oxygen, or another way to think about it is if you had 1 mole of oxygen molecules, you would have 2 moles of oxygen atoms. So this right here is the stoichiometric step. It's a step that we didn't have to do when we set up this problem, right? What we have to do is convert moles of the given substance to moles of the desired substance. We were given moles, we have moles of oxygen molecules, but we want moles of oxygen atoms, all right? And so this is the stoichiometric step. This is using our recipe and following the recipe. I know that there's 2 moles of O for every 1 mole of O2. That's going to cancel out moles of O2 and give me moles of O. And now, if I multiply moles of O by Avogadro's number, that's going to be atoms. So I get 2.69 times 10 to the 24th atoms of oxygen. Okay? So right there, that's that new calculation. That's stoichiometry. Using your recipe to do a conversion to go from moles of one substance, O2, to moles of something else, O. That's stoichiometry. Okay? So there's different types of stoichiometry. There's composition stoic, there's reaction stoic. It doesn't matter. You don't have to know which is which. The difference is what recipe are you using. Composition stoic, you're using a chemical formula for your recipe, like this was our recipe, and so we were able to figure out that ratio here in this step, 2 to 1, based on the recipe. So composition stoic is you're asked about a specific element in a compound, right? So I'm talking about a specific type of atom in an oxygen molecule, right? O, all right? There's also reaction stoic. Now, the difference between them, we're still going to follow the same steps. The difference between them is what the recipe is. So again, in composition stoic, we have oxygen, or we have a chemical formula as our recipe. But in reaction stoic, it's going to be a balanced chemical equation. And the important numbers to know in your balanced chemical equation are the coefficients in the balanced chemical equation. That's how we're going to get our conversion ratio to go from moles of one thing to moles of something else, using the coefficients in the balanced equation. So you don't have to really differentiate between reaction stoic and composition stoic, because again, as long as you know it's stoichiometry, you're just going to follow 4 steps and you'll be good to go. All right. All right. So here is a balanced chemical equation, right? The combustion of propane. So there's a lot of different ratios we can get this, but this is how we're supposed to read the recipe. For every 1 mole of propane burned, I'm going to get 4 moles of water. For every 5 moles of oxygen that undergo this reaction, you get 3 moles of CO2. You can compare anything in the reaction. You could say if 3 moles of CO2 are produced, then that means 4 moles of water were also produced. You could say if 5 moles of oxygen react, then 1 mole of propane also reacts, right? It's a 1 to 5 ratio or a 5 to 1 ratio. It's a 1 to 4 ratio or a 4 to 1 ratio. It's a 1 to 3 ratio or it's a 3 to 1 ratio. Then you could go to oxygen. It's a 5 to 4 ratio or a 4 to 5 ratio. and it's all mole ratios. So here are all the different ratios. Now, these aren't all the ratios, but here are some of the ratios we can get from this balanced equation. And you're going to choose the right ratio based on what you're trying to cancel out and what you're trying to go to. Think in terms of dimensional analysis. You would use this ratio if you had moles of water and you wanted to cancel out moles of water and get moles of propane. You would use this ratio, you would flip that ratio if you had moles of propane and you wanted to cancel that out and get moles of water, right? We would use this ratio here to cancel out moles of water and get moles of oxygen, okay? So you can get any mole ratio from the balanced equation, okay? So it doesn't mean you use all the mole ratios from the balanced equation, right? We could go 1 to 5, 5 to 1, 1 to 4, 4 to 1, 1 to 3, 3 to 1. Then we could go 5 to 4, 4 to 5, 5 to 3, 3 to 5. Then we could go here and say 4 to 3 or 3 to 4. It really just depends on what the question's asking, what you already have, what you're trying to cancel out, what you're trying to go to. All right. So let's look at a reaction stoic problem. All right. So it's asking how many grams of water will be produced if 25 grams of propane react with excess oxygen. So a couple things I want to point out here. So the first thing is, how do I know this is a stoichiometry problem? So remember, you're given the amount of one thing, you're trying to find the amount of something else. So here, we're given grams of propane, C3H8, but it's asking for grams of water. Given the amount of one thing, asked for the amount of something else, stoichiometry, all right? That's what I'm doing, okay? So what we're gonna do is take our given amount and convert it to moles. So I was given 25 grams of propane. How do I convert that to moles? I divide by the molar mass of propane. So grams of propane cancel out, and I'm left with moles of propane. Once I have moles of the given substance, now I'm gonna find my ratio in my recipe. Remember, the question is, I want water. Let me make this a little smaller so we can see the whole thing. I want water, and I have propane. So if we go to our ratio, the ratio is 4 moles of water for every 1 mole of propane. And I'm getting that from these coefficients, 4 moles of water for every 1 mole of propane. Okay, so again, grams of propane to moles of propane. Now, this is the stoichiometric step. Using my recipe, if I multiply by 4 and divide by 1, moles of propane are going to cancel out. That's going to give me moles of water. And then the last step is to convert to desired units. Once I have moles of water, I got to convert to the units that the question asked for. So now I have, since it asked for grams of water, I have to multiply by the molar mass of water. So 18.02 is the molar mass of water. So I'm going to do 25 divided by 44.11 times 4 over 1 times 18.02. And that will give me how many grams of water will react or will be produced if 25 grams of propane react. Now, another thing I want you to note here is they told us that we had excess oxygen. And so what they're telling you there is don't worry about the oxygen. It's like once you run out of propane, the reaction stops. If we had a fixed amount of oxygen, then we'd have to figure out which reactant runs out, right? We can only, 1 mole of propane can only make 4 moles of water if we have 5 moles of oxygen. So what they're saying here with the excess oxygen here is, hey, you got enough oxygen. You have enough oxygen to react with this much propane. So it's the amount of propane that's going to limit how much water can be produced. Okay? All right. So let's look at the steps. So these are the steps for any type of stoichiometry, whether it be composition stoic or reaction stoic or solution stoic. And all solution stoic could be composition, it could be reaction stoic. It just depends on, all solution means is now you're dealing with molarity calculations, okay? But anyway, so step 1 is know your recipe. So either have your balanced equation or your chemical formula written so you can look at the subscripts for the chemical formula or the coefficients for the balanced reaction, okay? The second step is take your given amount and convert it to moles. So notice, like in this case, we were given grams of propane. The first thing I did was convert it to moles. You always want to convert to moles. Take your given amount and convert it to moles, all right? Step 2, use the recipe. Follow the recipe. This will be the stoichiometric step. That's why I started here. It's the stoichiometric step. It's going to be your conversion. It's going to be using your recipe to convert amount of the given substance, moles of the given substance, to moles of your unknown. So here, what did we want? We wanted water. So water was our unknown and propane was our given. So we put the coefficient of the given substance on the bottom, 1, and we put the coefficient of what we were looking for on top. That cancels out moles of the given and gives us moles of the unknown, right? And so moles of the unknown are coefficient of the unknown on top, coefficient of the given on the bottom. Okay. And then the very last step for Stoic is convert to desired units. So after you do step 3, you have moles of the unknown. And so if the question asked for moles of water, you could have stopped at step 3, right? So if the question up here had asked for how many moles of water would be produced, we wouldn't do this last step. We would stop there. And once we did all the math here, we would have moles of water. But the question asked for grams of water, so we have to do one more step. And that last step is convert to your desired units. But again, remember, if your desired units are moles, you're done after step 3. All right? So let's try this one. How many hydrogen atoms are in a 10-gram sample of benzene? So this would be composition stoic because our recipe is the chemical formula of benzene, C6H6. And so what I have to know from this is for every 1 mole of benzene, there's 6 moles of H, 6 moles of hydrogen. Okay? And so that's going to be my stoichiometric ratio. All right? So step 1, take given, step 1, know the recipe. Step 2, take the given amount and convert it to moles. So 10 grams of benzene divided by its molar mass. So that's right there, that's the molar mass of benzene. Step 3, mole ratio, right? Recipe. And we get that from here, 6 H's for every 1 benzene. So that's going to cancel out moles of benzene and give me moles of H. And then convert to desired units. We wanted to know total hydrogen atoms. So once we have moles of an element, if we multiply by Avogadro's number, we'll get atoms of that element. So there is our final answer. Okay. Let's go to the next one. Here we have solution stoic, but it doesn't matter. It just means you're dealing with molarity. Still follow the same steps. So it says when 25 milliliters of a 1.5 molar solution of lead 2 nitrate is mixed with excess sodium chloride, what mass of precipitate is produced? So we'd have to kind of predict the products and do all the stuff we learned from unit 6. But this would be our balanced chemical reaction, right? Lead 2 nitrate and 2 sodium chlorides yield lead 2 chloride. That would be our precipitate. And we get 2 sodium nitrates, okay? All right, so step 1 is our recipe. So there's our recipe. And we needed to identify the precipitate here, right? Because if we know what the precipitate is, we can figure out the molar mass of the precipitate, and we're going to need that because we want to know what mass of precipitate was produced, right? So step 2, take given and convert it to moles. Well, when I'm given a volume and a molarity, you do liters times molarity gives you moles, right? So this is what that looks like. So we'd have to convert our 25 milliliters to liters. So we take 0.025 liters times the molarity. Remember, molarity is moles per liter. That's going to cancel out liters and gives us moles of the lead 2 nitrate. This one's an easy mole ratio. It's a 1-to-1. 1 mole of lead 2 chloride for every 1 mole of lead 2 nitrate. It's a 1-to-1 ratio. Boom, 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 right there. That'll cancel out moles of lead nitrate and give us moles of lead chloride. And then the final step is convert to desired units. We wanted the mass of the precipitate, so we'd have to calculate the molar mass of lead 2 chloride and put it there, multiply by the molar mass of lead 2 chloride, and we get 10.4 grams of lead 2 chloride. Okay. So let's look at our final example here. And this is what I want to show you is you don't have to, every stoichiometry problem, you're not going to have to do all the steps. Some of the steps might be done for you. So notice right at the top of the question, they gave me the balanced equation. So I already know what my recipe is. All right, I already know my recipe. So step 1's done for me, okay? They say if 9 moles of CO2 are produced, then how many moles of oxygen are consumed? So step 2's already done for me because step 2, remember, is take the given amount and convert it to moles. Well, they gave me moles of CO2. So that's done for me. So move to step 3. So all I have to do is take the moles of CO2 and multiply it by the mole ratio. That's going to give me moles of oxygen. So we go to our coefficients, we put 5 moles of oxygen on top, we put 3 moles of CO2 on the bottom. Moles of CO2 will cancel out, and we'll do 9 times 5 divided by 3, so we end up with 15 moles of oxygen. So all we had to do for this question is take 9 and multiply it by 5 over 3. And sometimes you can do the stoichiometry in your head. You don't have to show the setup, especially when everything's done for you, right? The only thing we had to know to do here was take this 9 moles, and multiply it by 5 over 3 to get our answer, right? Using our recipe. Okay? Okay. So that is stoichiometry, right? That's what you do. It doesn't matter if we label it as composition stoic. It doesn't matter if we label it as reaction stoic or solution stoic. It's just know the recipe, convert to moles, then use the recipe to convert from one substance to another substance, and then convert from moles of what you were looking for to, whatever units the question asked for. So maybe you got moles of a gas and it's at STP and they want the volume, so then you multiply by 22.4. So it's know the recipe, take given, convert to moles, use the recipe, right? Figure out the mole ratio from the recipe to convert from moles of the given substance to moles of the unknown substance, and then convert to desired units. Okay? Those are your 4 steps for stoichiometry. Okay? And so it just takes practice, and once you see a bunch of stoichiometry problems, you get used to it and be like, yeah, that's stoichiometry, or no, that's just a mole calculation. Okay? And so it just takes practice. So start practicing.